Hey everyone, and welcome back to Prefusion. I'm Anish, and today we'll be starting the types of compensator. So we have already covered the lead compensator, and in this lecture we'll study the lag compensator, the lag lead compensator, and the lead lag compensators. Okay, these three compensators we'll study. So let's basically start with lag compensator. So before starting, what did we study in the lead compensator? A lead compensator basically adds a phase lead to the system. Okay, it helps in stabilizing the system. Okay, it helps in changing the parameters of the system. So this lag compensator adds a phase lag. So when do you need to add a phase lag? When do you need to add a phase lead? All that we'll understand by questions. Just I want to give you a basic concept of the lag and lead compensator. So the lead compensator was like a causal approximation of the PD controller. So it will help us to change the performance domain parameters. The lead compensator, if it is a causal approximation of the PD controller, and this is like almost like a PI controller. You can think of it like that. That this will help us in reducing the steady state error. Okay, so yeah, so this adds a phase lag to the uncompensated system. It is used to attenuate high frequency components of the response. Okay, so it attenuates high frequency components of the response. That means it behaves as a low pass filter. Just hold on a second, let me check everything is recording or not. Okay, yeah, this is recording, and this is also recording. Fine. So this acts like a low pass filter. This acts like a low pass filter. So the transfer function, controller transfer function is like this: kc into s plus 1 by tau, s plus 1 by beta tau, where beta is greater than 1 and tau is greater than 0 and kc is greater than 0. Okay, like beta is same as alpha only, but like the transfer function is almost same. Here instead of alpha we have beta here, and beta is greater than 1. There alpha was less than 1, so we choose another variable beta which is greater than 1, because if we choose same variable alpha, then there will be some confusion, because alpha there it was less than 1, here it is more than 1, then there will be some confusion. That's why we choose a new variable known as beta. So what does this controller transfer function introduce? This introduces a open loop open loop 0 open loop 0 at sz equals to minus 1 by tau, and open loop pole at sz equals to minus 1 by beta tau. Okay, so this introduces a open loop 0 and open loop pole. Okay, so okay, I should write this open loop pole. Now, like, what is the pole 0 diagram? So here, what do you see? Beta is greater than 1. So beta is greater than 1. So this will be somewhat low value. This whole thing will be somewhat low value if beta is high. Hence, it will be more closer to the origin than this 0. So 0 will be further away from the origin. So for lag compensation, the pole will be nearer to the origin. So if a system is having lag compensation, then it is a pole dominating system. Dominating system. Okay, then it is a pole dominating system. So now let's obviously again do the same thing, analyze the control transfer function. It will be almost same, the magnitude is same, only that the magnitude is here of j omega will be, so this I can multiply this beta tau and this tau, so tau will get cancelled and beta tau will be only remaining here. So it will be kc beta and under root omega tau square plus 1 and omega beta tau square plus 1. Okay, so yeah, this will be my magnitude. Now again, my phase angle, the formula will be same like the previous case, but things will be bit different. So phase angle will be simply tan inverse omega tau minus tan inverse omega beta tau. Okay, so yeah, this will be the values for the angle. Now what are the corner frequencies in this case? So the corner frequency, obviously first we will get pole, so pole will have a corner frequency of omega p. Like this is used to draw the Bode plot, basically that's why I am doing all this. Corner frequency omega p will be 1 by 1 by beta tau, and omega z will be 1 by tau. Okay, so this is omega p and omega z. So these are the two things. So obviously the pole will come first in the Bode plot. This will come first, then 0 will come. Okay, then 0 will come. So how will the Bode plot look? Okay, so the Bode and the phase plot rough I will draw. So first you will get a pole, so obviously we'll get a phase lag at that instant, and the slope will also be minus 20 dB per decade. So this is my magnitude of GC of J omega, and this is omega. Okay, and this is this is, then we'll get a slope. Like here we got a corner frequency, and again at the end we got a 0. So this frequency is 1 by, I will write this frequency at the end, or else we can write this now only. Let me write this in the phase plot itself, that will be much easier. Or no, we can write this here. So basically, if I approximate my Bode phase plot, this will be something like this. 10 times something before this I will get a pole, so my slope will reduce. Okay, and the effect of this will go away. Somewhere around here it will remain constant again. Okay, again the effect of 0 will come up, and this will go towards 0. So the Bode phase plot approximately would look like this, and let me mark the poles and zeros. Let me mark the corner points. So this is 1 by beta tau, like this point, and this point is 1 by tau, and this point is 10 times more than this, and this point is 10 times less than this. So this point is 1 by 10 tau, and this point is 1 by, sorry I made a mistake, this is 10 tau, actually 10 by tau, and this point is 1 by 10 tau, and this point is 10 by beta tau, and this point is 1 by 10 beta tau. Okay, so these are the points, important points here. So you can see, like I am getting a here slope of minus 20. Okay, something happened, just hold on a second. Okay, this is like getting weird, acting weird now. Minus 20 dB per decade, and this is acting like plus 45 degree per decade. Sorry, this is not plus, this is minus 45 degree per decade, and this is some angle. Okay, we don't know, like the maximum 5 m also this can reach. So this is some angle, maximum angle that it will reach, and here this is plus 45 degree per decade. Okay, so yeah, what we can see that as the frequency increases, the magnitude is reducing, hence it is attenuating the high frequency components. Here it is attenuating the high frequency components, attenuating frequency components. Okay, so now what is this and this? So basically this is the gain at DC frequency, this is Kc beta. So this in dBs will be 20 log Kc beta. And this will be like at high frequency, what will happen, this beta will be in the denominator, so this will get cancelled and this will only remain Kc. So this will become 20 log Kc. Okay, so yeah, this is the thing. In dBs. So yeah, this is the Bode plots. Bode plot for a lag compensator. Bode plots of a lag compensator. Okay, so yeah, these are the things. So basically these are my few points about the lag compensator. Now we will like read a few key points. Basically it behaves as a low pass filter, as we saw from the Bode plots, reduces the steady state error. This is like a you can assume think like this is like a integrator, sorry, yeah, PI controller. So this reduces the steady state error. Now the bandwidth gets reduces. Why does the bandwidth gets reduces? Because the what is it doing? It is attenuating, right? As the frequency increases, it is attenuating. Hence, let's say my initial bandwidth was this. Now it is reducing the gain, so it is reducing the unity gain, or it is reducing the 3 dB down gain. So it is reducing this gain further of the original system. Then what will happen? Original system bandwidth was like this. So let me draw something. So original system was something like this, okay, and the bandwidth was something somewhere around this. The bandwidth was okay, let me draw this correctly. Let me name the original system like this. So the bandwidth was around here, okay. Now what is happening? We are reducing the gain. So if you're reducing the gain, this point will shift down further, this point will shift down further. So obviously this point will also shift down further. So what is happening? The bandwidth is reducing as this frequency at which it is going down from the like here no change in the gain. So here the gain change won't be there, but here there is a gain change, the gain is reducing. So obviously DC gain is fine, it is constant, but at higher frequencies the gain is reducing. That's why this will further attenuate. So obviously the 3 dB down point, okay, will come much faster than this, okay. So yeah, that is why the bandwidth will get reduced, or you can prove it, derive it directly, okay. And steady state error will reduce, that also we can understand, like this is like a PI controller only, okay. That's why I told you to think like that, okay. Also stability is reduced. Why is the stability reduced? Because what, like in PI controller stability also gets reduced, here also it will get reduced because the phase margin is reduced, because you're adding a phase lag, okay. So phase margin is reduced, the margin is reduced, so you're near to the 0 degree phase margin. So that is very not good. that is not good. Okay, so why stability reduce? The phase margin reduces because you're adding a phase lag with it. You're basically adding a phase lag. Okay, so phase margin is reduces. Phase margin reduces. Okay, why is bandwidth reduced? Low frequency gain no change. High frequency gain attenuation. Okay, so how does it reduce steady state error? We can prove it, like derive it. Okay, or like just it's, you can like intuitively think like there is a approximation of a PI controller and it behaves like a low pass filter. That just we saw from the border plot. That is just what we saw. Now at what frequency my phase will be minimum, basically minimum in the sense like negative direction maximum. So obviously I will not derive. Okay, but this will be same only. Omega m will be basically GM of the two uh, corner frequencies, beta, which is the GM. You can remember like this, that it is a GM of the two corner frequencies. Okay, and now what is sine phi max? Like what is my maximum phase angle? Maximum phase like frequency at which phase is maximum, that is fine. But what is my maximum phase angle? Phi minimum this time. Phi minimum in the negative direction, obviously. Phi minimum is sine inverse, again the same formula. You don't have to remember anything else. This is the same formula, just instead of alpha you will write beta. And why does the same formula work? Because if you understand this correctly, that beta will be greater than 1. So if beta is greater than 1, that means that this will be something negative. So if this is negative, what does that mean? That means this like this is negative and this is positive, hence you will get some negative angle. So that's why it's fine. That's why this formula is same only. So but how to remember this? But first I will explain that as this is negative, or this is 1 minus beta is less than 0, or beta is greater than 1, hence this will give me lag. This will give me lag. That is the first thing. Next thing is how to remember this. So overall magnitude cannot be ever more than 1. It will be always less than 1 because you are taking the sine inverse of that. So obviously if you are taking sine inverse, then sine theta should be something less than 1 or equal to 1. It can't be like the overall magnitude of that can't be more than equal to 1, because sine theta will always be something less than minus 1 or plus 1. Okay, something will always something less than this, the magnitude of this. Sorry, I should write this like this. The magnitude of sine theta should always be something less than 1, right? Magnitude of sine theta, so always less than equal to. So that's how you remember this. Okay, very important. That's how you remember this. Okay, so yeah, this is how you remember this. Like first thing is this is obviously negative and this is positive. Okay, so if this is negative and this is positive, what does it mean? So it means that your like what is sine theta? Sine theta is something like this, right? This is your x, this is your y, and sine theta will be this is, if this is the base, then sine theta, this is the like theta is measured from here, sorry. So sine theta will be something y upon this hypotenuse, so basically your y coordinate is negative here, y component is negative. Okay, y component is negative and x is still positive, y component is negative, this is the hypotenuse, x is still positive. So you are lying around here, like hypotenuse cannot be ever negative, so you are lying and in this quadrant, in the fourth quadrant, and in the fourth quadrant your angle is negative. That's why the angle comes up to be negative. Okay, I hope you understand. Y is represented by this upper thing and this is positive only. Okay, so yeah, this is about the phi minimum. Now let's do the standard circuit diagram. Okay, sorry, standard circuit diagram of a lag compensator. So previously it was providing some lead, so if it is providing some lead, so capacitor always will come here. Okay, if you like when you will study analog circuits, you will see the differentiator, the capacitor will come around here. Okay, and it always differentiator provides a lead and integrator provides a lag. So integrator will come at the output, and the capacitor will come at the output for integrator, and capacitor will come at the input for the differentiator. Okay, here capacitor is at the output, that means it is like a integrator, it is like a lag compensator. So now again, like same thing, let's derive few things. So if I derive few things, this will be R1, this will be R2, this will be 1 by CS, this will be V naught of S, this will be Vi of S. Okay, and like I just did the Laplace transform of this. Now if we just again do the simple voltage division, so if you do the voltage division, V of S equals to Vi of S into R2 plus 1 by CS divided by R1 plus R2 plus 1 by CS. Okay, so this is the case. So VO will be equals to VO by Vi of S will be equals to simply R2 CS plus 1 and R1 plus R2 into CS plus 1. Okay, so now what should we do? We have multiplied CS. Okay, so CS will get anyways cancelled, that is fine. Now what we can do this is we can simply like compare with the standard circuit, standard thing. So there the S coefficient was 1, so I will convert this S plus 1 by R2C, R2 times C, and this is S plus 1 by R1 plus R2 times C. And yeah, R2C, and this I am taking common, so obviously I have to write this. So C will get cancelled, C will get cancelled. Okay, and this will be R1 plus R2 only. Okay, so now let's compare with the standard equation of standard transfer function of this controller, which is this one. So basically what we can say here that my Kc is R2 upon R1 plus R2, and what is my tau? Tau is CR2, and my beta will be simply R1 plus R2 divided by R2, because it will be always more than 1. It will be always more than 1. From here also we can see that beta is more than 1. Like this also you can remember how does my beta come up. So this is a standard circuit. In case of standard circuit, the capacitor will always be towards, if it's a lag compensator, the capacitor will always be towards the output, and if it is a lead compensator, the capacitor will always be towards the input. Okay, so these two things you have to directly keep in mind. Now this is the tau CR2. Okay, and this is how you remember that simply CR2 is a time constant here, right? Okay, like there isn't any other method, like time constant of this is simply this tau. Okay, just with intuition you can remember this. So this is how you remember the beta, and if some non-standard question come up, you have to derive it by yourself. So we can observe that Kc is something less than 1. Okay, something less than 1, that is what we observe, that at high frequencies what is my gain? My gain is 20 log Kc, which is less than 1. Yes, this is satisfying, and at low frequencies my gain is this Kc times this, which is 1. In this case, like, my gain is 1, because if you compare the high and low frequency, you will see. So let's just compare that thing. So at low frequency, what is happening? Low frequency, this is going open circuit because S equals to 0, so this is giving me infinite impedance. So at low frequency, no, this is giving infinite impedance. That means my Vi, whatever comes over here, no current is flowing through here, so obviously 0 drop, so this Vi will directly come across the output Vo. So Vo of low frequency, Vo will be equals to Vi at low frequency. So this is the low frequency region. Low frequency region at S equals to 0. Okay, so Vo is equals to Vi, that is the ratio of Vo by Vi is 1. Ratio of Vi over Vi is 1. Now what about the high frequency region? What about the high frequency region? The high frequency region is basically when the frequency is very high, infinity. So if it is infinity, obviously this capacitor will get short circuit, because 1 by Cs, 1 by infinity is 0, 1 by infinity is 0, so this is going to be short circuited. So 1 by 0 was infinity. So let me write at S equals to 0, it is equals to infinity for the previous case also. I maybe have forgotten, yeah, I've forgotten this case. So here I should write so at high frequency region, what will happen? High frequency region, this will get short circuited, so it will be something like this. So simply it will be a voltage division. So Vo will be equals to Vi into R2 by R1 plus R2. R2 by R1 plus R2, which is less than 1. Here. High frequency, yeah, R2 by R1 plus R2. Okay, so which is less than 1. So like this also you can recognize whether this is a low pass filter or high pass filter. In this case, this is a low pass filter, because high frequency it is attenuating and lower frequency it is giving me one gain. So low pass filter is like a lag compensator, and high pass filter is like a lead compensator. So you can recall like that also. Okay, so yeah, this was it for the lag compensator. Now let's go to the lag lead compensator. So lag lead compensation combines the effect of lag compensation and lead compensation. Okay, and like, what does lead compensation do? So let me mark these individual points. What does lead compensation do? So lead compensator improves the stability margins and the transient response, but may decrease the steady state accuracy. So lead compensator improves the stability margins and the transient response, but may decrease the steady state accuracy. Okay, lag compensator attenuates the high frequency components. Sorry, there has been some typo. High frequency components that may reduce the system stability. Okay, so that may reduce the system stability, but what it does is it increases the steady state accuracy, but it increases the steady state accuracy. Okay, so lag compensator attenuates the high frequency components that may reduce system stability, but it increases the steady state accuracy. It increases the steady state accuracy. Okay, and lead compensator does all these things. So let's now like draw the controller transfer function. Write the controller transfer function first. So for a lag lead compensator, basically what will happen is it will combine the effects of both. So there will be two poles and two zeros. So let me just write the transfer function. GC of S. Okay, GC of S equals to KC into S plus Z1 into S plus Z2 divided by S plus P1 divided by S plus P2. So basically two zeros and two poles. Now out of this, what I will do, I will separate these two out. Okay, I will separate these two out. So out of this, this will be my, like I can name this as, this will be my lag compensator. This will be my lag compensator, and this will be my lead compensator. Okay, and combining these two, I will get lag lead compensator. Now combining any lag and any lead compensator won't give you lag lead compensator. They have to be particular. How particular? Like their pole zero diagram should be something like this. If you're combining a lag compensator and lead compensator, their pole zero diagram like should be something like this. That the pole of this one should be first, then the two zeros of both of them, like after combining both of them, will lie in between the other pole. So then only this will be a lag lead compensator. Okay, just combining any lag compensator and any lead compensator won't cut it. Just be careful about that. So this is the lead compensator, as this is further away. Okay, and this is the lag compensator as this is near. Okay, lag and lead compensator. So here we can see that it is giving me both lag and lead compensation. Okay, in the Bode plot we'll be able to understand it better. But for a lag lead compensator, what will happen is we can see the pole is much nearer to the origin. Okay, so that is like how it is defined. So if pole is much nearer to the origin, obviously it will give phase lag. That's why we first write this lag. So it will provide me lag first, then it will provide me lead. So it will be a lag lead compensator will be a pole dominating system. Lag lead compensator. Pole dominating system. Okay, so it will be lag lead compensator if the pole is near to the origin. So like how will we draw the Bode plot? Obviously drawing the phase plot will be very complex, so I won't draw it, but we can definitely draw the Bode plot with the help of the pole zero diagram. I'm not like writing the magnitudes, the value of the magnitude at the frequency. I'm just drawing the Bode plot, rough Bode plot. So obviously DC gain is some constant value k. Okay, here we have some constant. It is not k actually. Z1 by P1, Z2 by P2. If you write in time constant format, it will be Kc. Okay. So then what will happen? We'll get pole first. Pole will come first. So I will my slope will reduce first. Then I will get a 0. So obviously it will become constant. Okay, slope will be 0. Magnitude will become constant. And then again I will get a pole at the end. Okay, I will get a pole at the end. So no, sorry, I will get a 0. Like after this 0 I will get a 0, then after that I will get a pole. So 0, and then I will get a pole. So obviously my slope will again become 0. So here what is my slope? 20 dB per decade, and here my slope is plus 20 dB per decade, and here my slope is 0 dB per decade, and here my slope is 0 dB per decade. Okay, and here also my slope is 0 dB per decade. So yeah, this is P1, this is Z1, this is Z2, this is P2. Okay, so P1, Z1, Z2, P2. So these are the things. So this is the magnitude. Now like this is the border plot. As you can see, right, this is like a what, notch filter, right? If you recall correctly, the amplifier, like if you have studied analog circuits, you will know this is like a notch filter if you draw it accurately. So yeah, it is like a band stop filter, band reject filter. It's like a band reject filter. If you don't understand, don't worry, you will study all this in analog circuits. It's like a band reject filter. I will write this all later on also, band reject filter. Okay, so like what is a band reject filter? Basically a band reject filter, the filter characteristics is something like this. Omega, this is magnitude of Gg omega, and if it is an ideal band reject filter, then it will have a stop band. It will like be like a square shape. It will be like this. So here it is a low pass filter. It is a combination of low pass and high pass filter, but the pole placements are very important. The cutoff frequency of the low pass filter will be lower than the this cutoff frequency, right, of the high pass filter. So not the cutoff frequency, the like the point where the high pass filter starts to provide some gain. So very important. So yeah, cutoff frequencies are very important. So this is the stop band basically. This is the stop band. Stop band. Okay, so yeah, this is the thing about this filter. And like if you want to do this like in non-ideal manner, this will be like a notch filter. Like the actual practical notch filter will be something like this. If I draw this in front of this, it will be something, let me draw this. So this is a notch filter. It is like a notch. If you just see your mobile phone, right, previously your mobile phone, your front camera, it's like a notch. If few phones have that, now it's a punch hole, right? Directly you just see the circle of the front camera now, the latest phones. But if you see some older phones, it will have a notch like shape, like a wavy thing near the front camera. So that is what a like a notch means. Okay, so yeah, this is the this thing. So like let's like draw, this is a standard diagram of a lag lead filter. So here what will happen, the circuit diagram will almost be same for a lead lag and a lag lead, but the difference will be for a lag lead we'll get lag. So the lag circuit diagram will be almost same and lead circuit diagram will be here, right? So lag will be towards the load and the lead will be towards the input. Now for lead lag, the lead will be towards the output and the lag will be towards the input. So here I will mention this, how to remember the circuit diagram. So basically in this case, lag, this is the lag compensator, right? So lag is towards the output, and lead is towards the input. Lead is towards the input. Okay, so this is the so basically this is for a lag lead compensator. Let me write this here. Just hold on a second, let me drink a bit of water. Yeah, so for basically this, so what one thing I wanted to do is the homework. Basically, until now for lag compensator and lead compensator, we have been deriving the transfer function. So the homework for is to derive the transfer function for this lag lead compensator. Okay, that is the homework for you that you do. Okay, now I will just do the simple low frequency and high frequency regions approximation. So at low frequency, what should happen? I should get some finite gain, and at high frequency I should get some finite gain, and in between my gain should reduce. So at both of the end of the spectrums I should get some gain. Okay, so if I get some gain at both of the end of the spectrums, either it can be a band stop filter or it can be all pass filter. So in our case this can't be all pass filter because all pass filter can't be realized with passive components, so the only option is band stop filter. Okay, so if you didn't understand anything, don't worry, all this you will study in the analog circuit, don't worry. Okay, so let's analyze the high frequency and low frequency region. So at low frequency s equal to 0, what will happen? The capacitor will be open circuit because 1 by cs 1 by c1s, so basically 1 by 0 is infinity. So infinity impedance, this is open circuit, this is open circuit, only this R1 and R2 is present. So if I just copy this circuit, so this will be gone and this will be gone. Okay, hence R1 and R2 will be present, no current flows through here, no current flows through here, so zero current through here. So this whole thing will come at this node, so obviously V0 will be equals to Vi. So for low frequency region, Vi of t. Okay, so I should write V of at low frequency region. Okay, then what is happening at high frequency? At high frequency, basically this capacitor will get short circuit and this will also get short circuit. Basically what will happen, again V0 will be equals to Vi. Let's see, let's first draw the circuit. Okay, let me take this to the next page. So if I take this to the next page, this I delete, this I delete, this is short circuit, this is short circuit. So this point directly comes at this point, so your Vi will be equals to Vo. Okay, so Vi will be equals to Vo. So this is Vi. So basically again my Vo will be equals to Vi. So I forgot to wrote here one thing, that Vo by Vi equals to 1. So if Vo by Vi equals to 1, what does that mean? That means that I am getting some finite gain. Okay, so no attenuation, and here also again Vo by Vi equals to 1, again no attenuation. Okay, so we don't get any attenuation. So next from this we understand, yes, I'm getting finite gain at high frequency and finite gain at low frequency. Obviously this will be a band stop filter or a notch filter. So this will be a band stop filter or a notch filter. Okay, or a notch filter. Okay, so yeah, this is the case for this. So this is, if this is like performing like this, if the circuit is performing like this, then definitely it will be a lag lead compensator. Now let's study about the lead lag compensator. For lead lag compensator, what will happen? Basically, for lead lag compensator, the zeros will come first. The zero will come first, then the pole. So here 0 will come first. Okay, first the lead compensator, then the lag compensator. So I have already drawn the pole zero diagram. Okay, something has been gone wrong here. I don't know what has gone wrong. So yeah, here what do you see? 0 and this. So 0 is first, then there is pole, then there is pole, then there is 0. So it will have to be arranged like this. It can't be like this, that yeah, 0 and pole is here, but then again 0 and pole. It can't be like this. Don't remember. Then it won't be a lead lag compensator. It will be something else. Okay. So this is the lead compensator. This is the lead compensator. This is the lag compensator. Lead and lag compensator. Okay, so here, as this is a lead compensator, hence this will be a, sorry, as this is a lead lag compensator, hence this will be a zero dominating first. So 0 will be near the origin, like obviously the name suggests itself that this is a lead compensator, lead lag compensator. So what is this? This is a 0. 0 is more nearer to the origin. As this is lead compensator, 0 will be more dominating. 0 dominating system. Okay, it is a 0 dominating system. So this is the case. Like if you want to draw the Bode plot, we can draw the Bode plot for this. So obviously 0 is coming first. So initially there will be some constant gain. Then it will have the transfer function will be same only. Transfer function will be same only, but just the poles will get swapped now. So let me copy this. Okay. So GC of J omega, and this is omega. Okay, so then what is happening? Then we get a, like, first my gain is constant, then at this corner frequency, what are the corner frequencies? At this Z1, like this minus Z1, what do I see? I see a 0. So I'll get a slope of plus 20 dB per decade, plus 20 dB per decade. Then this will be remain constant, this will remain constant. Then this will be 0 dB per decade, and this will be minus 20 dB per decade. And this will be again what is happening here? I'm getting a 0, hence the slope increases. Then after this I get a pole, hence the slope reduces. Again the slope, like I get another pole, I encounter another pole, so slope further reduces. Next at the end I get a 0, so slope increases. So this is 0 dB per decade. Okay, so this is omega, this is the magnitude of J omega. So this is like this, Z1 beyond. So what is the standard circuit for this? So we can see what type of filter is this. This is like a band pass filter, because it is not passing low frequency bands, high frequency band. It is only passing some band. Okay, like some band. It is only passing this band. Okay, everything else it is rejecting. So it is like a band pass filter. So this is like a band pass filter. So if you don't understand the filters, right, it is totally fine. All this will be taught to you in analog circuits in full details. So even here I am giving you the intuition. Why is it called a band pass filter? Because it is only passing it is passing components of particular frequencies. It is rejecting all the other components. Here the gain is very low. It is attenuating those. Okay, so that's why it is called a band pass filter. So like a ideal brick wall band pass filter will be something like this. That it will only perfectly pass particular frequencies and it will give zero gain for other frequencies. Obviously getting that ideal band pass filter is not possible. Okay, so these regions, these regions are known as stop band. And this region is known as the pass band. Okay, so this region is known as stop band and this region is known as the pass band. So like what will be a practical band pass filter look like? The frequency characteristics. So the frequency characteristics of a practical band pass filter is more or less like this. Okay, so it's just the opposite of the notch filter. So notch filter was passing all frequencies except that band, hence it is called as band stop filter, and a band pass filter is passing this band and rejecting all other bands frequencies. So yeah, this is the practical. Let me write here, this is the practical and this is the ideal one. Okay, this is the ideal one. So these are the things. So this is about all of the things. So but before that, obviously we have to again see the circuit diagram. So here again we see, right? So here what is happening? The lag the lead component is connected across the output and the lag component is connected across the input. So from here also you can understand it is a lead lag compensator. So yeah, that is. So here, just hold on a second. We see this is the lead component and this is the lag component of a lag compensator. So we can observe that lead is connected at the output and lag is connected at the input. Okay, lead is connected at the output and lag is connected at the input. So obviously through this you can understand that this is a lead lag compensator. So hence this is a lead lag compensator. Okay, so yeah, this is the case. So like I would again derive the transfer function. This is what you have to do by yourself. VO upon S by VI upon S equals to, that is what you derive right now. Okay, that is what you derive. So let's I will do the low frequency and high frequency regions. So like for low frequency, again the same thing will happen, that it will become open circuit. S equals to 0, it will give me infinite impedance. So this will become open circuit. So if this becomes open circuit, what will happen? Zero current is coming through here and zero current is coming through here. So zero current is flowing through here. Hence this has 0 volts of drop. Okay, so if this has 0 volts of drop, then definitely my VO will be 0 volts. VO will be 0 volts. VO will be equal to 0 volts for low frequency region. So this is for low frequency region at S equals to 0. Okay, now what is happening at the S equals to infinity? S equals to infinity at high frequency region. So at high frequency region, capacitors will get short circuited. So if the capacitor gets short circuited, what will happen? So obviously, again, this is short circuited, so this is 0 voltage drop, so VO will be again equals to 0. V equals to 0, so at S equals to infinity, this is getting short circuited, so VO will be 0 volts. Okay, so VO is 0 volts. Then again, like we are seeing that at high frequency and low frequency we are getting 0 gain. So obviously this is a band pass filter. So this is a band pass filter. Okay, so yeah, that is what this is. So did I write everything correctly? Yeah, band pass filter. So yeah, that is basically it for the theory part of lag lead compensator. So we'll do few questions and I will summarize quickly. Just one question I will do. Okay, and this question will clear up your mind about like what is a lag compensator, what is a lead compensator with the location of poles and zeros. We can identify the lag compensator and lead compensator. So yeah, just take the screenshot or you just pause the video and just try to attempt. You have to identify the type of compensation used from the location of poles and zero. So like there are two poles and like one pole and one zero, then two poles and two zeros, then two zeros and two poles. All these things are there. Okay, all these things are there and you have to identify the location of poles and zeros, right? So sorry, you have to identify the type of compensation used: lag compensation, lead compensation, lag lead compensation, lead lag compensation, what type of compensation is used. Okay, so yeah, you try to solve this, then I will solve this. So yeah, this is the ABC and this is the DEF. Just let me check everything is fine. Yeah, everything is recording. This is recording, this is recording, fine. So yeah, let me now do this. So basically compensation is designed using passive elements. Okay, compensation will, like in our case, what we'll assumption is, first assumption is compensation is used with passive elements hence it has to compensation is used with passive elements, hence it has to be a minimum phase system, basically minimum phase system where the poles slash zeros cannot lie on the right hand side of maze plane. Okay, so yeah, then obviously for it to be compensated basically, so here can I eliminate something? Here this is fine, pole and zeros are lying on the left hand side, that is fine. Here everything is lying on the left hand side, here also everything fine. But here what do you see? Here I see poles are zeros and lying on the left hand side, so this will not be a compensator obviously. So you can't say that zero is near the origin and this is a lead compensator. No, you can't say that. Okay, here this is fine, this is fine, this is fine. So that is the first trick, that is the thing that you have to notice. Are all the poles and zeros lying on the left hand side, then only we can use this as a compensator obviously. If no active elements aren't present, only passive elements are present. Okay, so that is one thing about this. So now let's solve each of them one by one. So the first one, let me just do one thing, let me just copy and paste these things, that will be much quicker for us. So for the first case, pole is at -1 and 0 is at -10. Okay, so obviously pole is near to the origin, so this will be a what? This will be lag compensator. Sorry, this will be 0. This will be a lag compensator. Okay, and next we have two poles and two zeros. So first pole is here and then 0 is here. So pole is here, then there is a 0. So it is z equals to -1 and z1 -2. Then we have a pole and a 0. Pole and a 0, -3 and -4. So basically what we see is, initially here this is like a lag compensator. So this will be a, as we have four, like two zeros and two poles, and this is initially we have a lag compensator, hence this will be a lag lead compensator. This will be a lag lead compensator. So if you nodded your head on that, then I should come to your side and give you a big slap. Why? Because I just told you that the poles and zero locations are specified, right? Poles, like that, either two poles should lie near to each other or two zeros should lie near to each other. Then only we can call them as lag lead compensator or lead lag compensator, like that, whatever. Okay, so here are, is that the case? No, that isn't the case. So obviously we can't say this. We can't say this. So this is not a compensator. This is not a compensator. Not a standard compensator. You can call it any compensator, but this is not a standard compensator. Okay, standard compensator. Let's do this C case. So the C case, Z1 P1, and this is at minus. So this is not, sorry, this is not at minus. So this is at -3 actually. So like -3 this is, so 0 at -3. So basically it's the same, only just the opposite case. So Z1 is first, then P1, then Z2, then P2. -1, -2, -3, -4. -1, -2, -3, -4. Yeah. Okay, so what is it? So you might think that this is a lead lag compensator, but again, like for the same reasons, this is not a lead lag compensator. Okay, so just what, let me do one thing, just take this to another page because this is taking up much more space. Okay, so now, like I will cross this obviously because this is not a lead lag compensator, because the pole zeros are not as defined for a standard truck. Okay, so no, not like a standard compensator, that's why. Okay, not standard. Again, like for the, this is the C case, and for the D case I already ruled out things, that here 0 and poles are lying on the right hand side. Obviously it can't be possible. It has to be a minimum phase system. So yeah, it has to be minimum phase system. Okay, not a minimum phase system, hence this is not a compensator. Okay, not a standard compensator, not a standard compensator. Okay, so yeah, let's now like go to the E part, just wait a second, let me see everything is recording or not. Yes, everything is recording because this has went on long. Let's now go to the E part. E and the F part. So the E part, what is happening? E part, obviously, I have both of, like 0 is at -1 and pole is at -10. Okay, 0 as -1 and pole is at -10. So this is basically what? This is a lead compensator, simple. Zero dominating system. Now here what is happening? I have a like 4 things. So 0, then pole, then pole, then 0. So this is following that pattern. So first I have a 0, then I have a pole, then I have a pole, then a 0, -1, -2, -3 and -4. So basically this is what, so initially this is acting like a lead compensator, so this will be a lead lag compensator. Okay, hence this is a standard compensator, hence this is true, lead lag compensator. Okay, so yeah, this is basically it about the questions. Questions were very simple, just few tricky things that you have to keep in mind, because gate is right now playing with few tricky things, right? So you have to keep those things in mind also. Now let's do the summary of compensators, whatever we have learned. So for a lead compensator, the pole zero diagram will be like this, and what type of filter will it be? It will be a high pass filter. Why? Because 0 is at the top, 0 is at the top, like 0 is dominating, 0 dominating, so the top one is dominating, hence for higher frequency we will get good gain. Okay, good gain, so that is why it is a high pass filter. And for lag filter, again the pole is dominating, pole is more near to the origin, hence what will happen, we'll get a good gain at the lower frequencies. Okay, low pass filter, hence it is a low pass filter. For high frequencies will go to 0, gain will go to 0. Again for lead lag, this is like you have to remember something, that it is like a band pass filter. Okay, for lead lag it is like a band pass filter that we just studied. Lead lag means lead first then lag. So the circuit diagram, lead is first. If lead is first, that means in the Bode plot I will get a plus 20 dB per decade, then it will be, then I will get a pole, it will be constant, then again it will do. So it is like a what? It is like a band pass filter. That is why you can remember with the Bode plots also. Band pass filter with the Bode plots. So just a thing to remember, how to remember. Okay, and for it, like one thing is remaining, lag lead, so obviously it will be band stop filter. But how to remember this? So it will be like this. Okay, so if you recall correctly, that first I will get a pole, okay, then I will get a 0. So initially my slope will be -20 dB per decade, then again it will go to plus 0 dB per decade, then it will increase to plus 20 dB per decade, then it will go to 0. So yeah, this is what a band stop filter is. Okay, so yeah, this is basically the summary of filters. And like, sorry, not summary filters, like filters you will study, but just giving you a brief overview about filters. And like compensators, this is a summary of compensators. And in the next lecture we'll do most all questions. So the theory part is over now, so we'll just do the questions on controllers and compensators, and that will be the end of this whole control systems. Okay, so yeah, I hope you like all of this series, and I will see you in the next video. Thank you for watching.